Hi everyone, we are Glenda and Erhn, presenting to you our project, Antivirus Autobots, predicting more infectious virus variants for pandemic prevention through deep learning. Over the past 2 years, there have been wave after wave of COVID-19 infections, with constantly emerging variants like Delta and Omicron. These variants arise from mutations in the SARS-CoV-2 spike protein, which increase its binding affinity towards the human ACE2 receptor or HACE2. These variants can evade our immune system and even infect vaccinated people, reducing vaccine efficacy. Current deep learning work has explored determining factors that drive virus mutations rather than predicting more infectious variants. Hence, we want to use deep learning to predict more infectious variants from an existing virus. This can help researchers develop vaccines that protect us against them before they strike, preventing future outbreaks and saving lives. We gladly present Optimus PPIme, our novel deep learning approach. Optimus PPIme comprises an agent which acts as a virus attacking a host cell. It aims to bind better to the host receptor to increase infectivity through mutations. The agent can substitute any amino acid in its sequence. The agent then interacts with a protein-protein interaction or PPI transformer network we developed. Given the primary sequences of a virus and host receptor protein, the transformer network outputs a PPI score with a high accuracy of 90%. The reward is the change in PPI score. Our research question is a PPI predictor environment sufficient for virus agents to predict future, more infectious variants? We hypothesize that given an environment which scores the binding affinity for a virus host PPI with high accuracy, agents can predict future, more infectious variants.
For our methodology, we first collect our PPI datasets in step 1. Next, we build our PPI transformer in steps 2 to 4, and lastly, develop our virus agents in step 5. To train our PPI transformer, we compiled positive and negative virus-human interactions from the databases here. For the novel virus test set, we fixed human ACE2 as a second input protein. Positive PPIs include the original COVID-19 spike protein and its 23 variants. We sampled 26 negative PPIs from non-coronavirus proteins. These were all inputs for our transformer. Initially, our transformer outputted the same value for all test data. This could be due to unbalanced dependencies caused by layer normalization. Although we were disappointed, we overcame this by pre-training our transformer with MLM, or mass language modeling. By learning the semantics of protein sequences, this could improve downstream PPI performance and enable our model to output different PPI scores. However, even after MLM pre-training, our transformer's test accuracy was only 44%. This is likely due to its complex loss landscape. Thus, we attempted sharpness-aware minimization, or SAM, for these 3 scenarios to generalize better to unseen proteins. SAM minimizes both loss value and loss sharpness, so the model learns weight with uniformly low loss values, shown by the smooth landscape here. To boost our test accuracies, we also attempted 3 protein augmentation techniques during MLM pre-training. The first is alanine substitution, which randomly replaces an amino acid with alanine, which is unreactive. Next, we reverse the whole protein sequence. Finally, dictionary substitution replaces random amino acids with one of the highest Blossom score or the most likely substitute. For instance, amino acid E has the highest score to D, so it will replace D.
Now, we arrive at our results. For models 1 to 2, although model 1 achieved the lower accuracy, MLM pre-training helped it to learn relevant protein features and output different PPI scores. For models 3 to 5, SEM on MLM causes the model to learn MLM-specific parameters, which may not be best suited for our PPI task. So, SEM on PPI is essential for optimizing our PPI task. For model 6 to 8, alanine substitution improved accuracy the most, as it alters protein syntax less drastically than reverse and dictionary substitution. Thus, our best model is model 8. Using model 8, all COVID-19 variants achieve higher PPI scores with HACE2 than the original virus, so the model can make predictions which corroborate with real-world data. Here's our confusion matrix. Our model correctly predicted all positives and 21 negatives.
With our PPI transformer complete, Autobots roll out. To propose future, more infectious variants, we attempted 3 algorithms for our agents: Deep Q Learning Network or DQN, Greedy Search, and Beam Search. DQN uses reinforcement learning to learn the best policy. However, after training for 6 hours, its final reward still did not increase, likely due to our large search space. Hence, we implemented Greedy and Beam Search, which are more efficient. To analyze the feasibility of our proposed variants, we generated the 3D structures and docked them with human ACE2. They do resemble the original. The variants from Beam Search attained higher PPI and more negative docking scores than the variants from Greedy Search, reflecting its greater binding affinity to HACE2. Why so? Greedy Search always exploits the best immediate action, while Beam Search balances exploitation and exploration. By considering 10 sequences each time step, it is likelier to find mutations that optimize long-term rewards from future amino acid interactions. The root mean square distance values, or RMSDs, of our proposed variants from the original COVID-19 spike protein are close to that of current variants like Omicron or Delta, so they are realistic. Hence, Optimus PPIme can propose future, more infectious variants, proving our hypothesis.
In conclusion, as prevention is better than cure, our deep learning approach can improve vaccine development and prevent new waves of infections. By changing the training data, our approach can also combat other viruses. In future, we plan to measure the infectivity of virus variants with antibody evasion and exclude mutations that destabilize the protein structure. Thank you.